So, meaning earlier on in the class. All right, so limit as x approaches 4. All right, so it's 2 fractions over a denominator. So it's 1 over x minus 1 over 4 all over x minus 4. Yes.
Because it's, how did I know? Because it's f of x minus f of a over x minus a. Good, awesome, great job. So yes, now this can be addressed with L'Hopital's rule. You have the tool. So it's 1 over 4 minus 1 over 4, the top is 0. 4 minus 4, the bottom is 0.
Right.
You can if you want to. So limit as x approaches 4. The top prime, please always remember this function, over 1, and you're done. But I couldn't show you in chapter 2 L'Hopital's rule, because we had to learn differentiation rules before doing this, before showing you L'Hopital's rule. And what is the limit?
Negative 1/16.
That's it. Absolutely. But remember, L'Hopital's rule is only 0 over 0 or infinity over infinity.
Yes.
Good.
And it's got to have the... Yeah.
It has to have the limit. So the conditions or hypotheses are limit a fraction that turns into 0 over 0 or infinity over infinity. Otherwise, you're not allowed to use this differentiation process unless it's inside a limit. And the initial assessment is 0 over 0. Good. L'Hopital's rule is in chapter 4, but I never wait till chapter 4. I always use it right after we learn differentiation rules. Good. Anything else? Next topic.
What about like the whole versus
yes,
like
vertical asymptote. Yeah, so if I have
jump.
Yes, so if I have, let's say, x squared minus 2x over
Which
x.
section is this? I'm sorry, do you remember?
Yes, so
2.5.
Yes, so this is in chapter 4.
Oh.
Yes, the graphs and holes and slant asymptotes and all the asymptotes are basically in chapter 4.
Okay.
So if this is a function, first of all, I have to find the domain, and the domain is clearly this, anything but these two. But then when I simplify it by factoring x in the numerator, then I realize that this goes away, but this condition remains. So therefore, x equals 0 will be a hole. In other words, removable. Discontinuity, to be exact. But it's a hole in the graph. By a hole in the graph, we really mean this. This is what we mean by a hole in the graph. Because that's what the removable discontinuity is. The limit from the left and the limit from the right are the same. However, x equals -1 stays as a vertical asymptote because the simplified form is x minus 2 over x plus 1. Please, 90% of the students, although I show this in class so many times, they come back to this to differentiate. No, this is gone, done and over with. You differentiate this to find f prime and then f double prime. You always differentiate the simplified form. You already removed this factor, it's gone. This is our new function, the simplified form, and we find f prime and f double prime.
Thank you.
Very good. Good question. Always some of my students get tripped by going back, and it takes forever to differentiate that. And if you don't simplify, you'll never get to the correct answer. Once a factor is gone, since you already stated the restriction, since you already know that is a whole, you cannot change that. And you know that x equals -1 is a vertical asymptote. Now you're differentiating only this piece, which is a piece of cake, right? Top prime is 1 minus the top times the denominator prime. You're done. 3 over x plus 1 squared. It will take forever to simplify the derivative of this to 3 over x plus 1 squared. And when you find the second derivative, that's even easier, because it will be -6x plus 1 to -3, or -6 over x plus 1 cubed. So don't go back here. It will take you a page, and you may not ever get to these two. And of course, in such a case, you have to determine that, show that y equals 1 is a horizontal asymptote. This is a pure rational function. It will have the same horizontal asymptote left and right. You don't have to determine both limits. So at infinity and -infinity is the leading coefficient over the leading coefficient, because they have the same degree. And you don't have to show both limits like we had a few minutes ago. That was a sophisticated situation with that e to the x. Okay? This is a sophisticated function. It's not a pure rational. And you saw it has y equals 7 horizontal asymptote at infinity, and y equals 0 at -infinity. Very good question. Thank you. Good. Next. Anything else?
Can we go through an example? It's from WebAssign. WebAssign 4.4, the indeterminate forms.
Yes. Any.
Okay, so the question.
Yes, any question.
Okay, so the question is, as the limit x approaches 0, and then it's tan open parentheses 7x.
Tangent? Yes.
Yep, open parentheses 7x, close parentheses, and then it's a fraction. So that, and the denominator is sine open parentheses 6x.
Perfect. So since tangent 0 is 0 and sine 0 is 0, we can use L'Hopital's rule. That's one option. It's not the only option. But if we do that, tangent prime is secant squared of 7x times the inner function prime. And sine prime is cosine 6x times the inner function prime. As x approaches 0, this is 1, this is 1, so the answer 7/6.
Okay, I see why I went wrong. I went one step too further.
Good. Next question. Anything else? Do you need help with anything else?
If no one else has one, I have another one, another example like that.
Absolutely, I'm ready.
Okay, so it's the limit as x approaches 1, and then open parentheses 7x in the numerator, and then in the denominator is x minus 1. And then that whole fraction is minus. It's two fractions being subtracted, yeah. And then it's 7 in the numerator for the second one. And then in the denominator it's the natural log. And then open parentheses x.
Perfect.
That's the whole equation.
So let me read it back to you, so making sure that this is okay. Limit as x approaches 1 and open parentheses 7x over x minus 1 minus 7 over natural log x.
Yes.
Perfect. So remember, I always say, always plug in to see what it is, unless, so this is one exception. We have to simplify and change this difference into one fraction. That's our first step. Why? Because 7 over 0, I don't know what that is. And 7 over 0, I don't know what that is. So this is one time, one exception in which I have to simplify. So I have to find the least common denominator, which has to be the product of these two. So this one needs a natural log x, and this one needs an x minus 1. So 7x natural log x minus 7x plus 7. Negative 7 times x, negative 7 times negative 1. Now I can assess the situation. The top, 0, 7, negative 7 plus 7, 0. 0 times 0, 0. I like it. Why? Because it's a limit, it's a fraction, it's 0 over 0 as our preliminary situation. So therefore, I can use L'Hopital's rule. So this is limit as x approaches 1. The top, this is a product. I have to be very careful here. The first function prime is 7 plus 7x times the second function prime, which is 1 over x, and minus 7. This is 0. Here I have to be very careful again, because it's a product. The first function prime is 1 plus x minus 1 times the second function prime, which is 1 over x. We continue. Do not drop the limit operator. We have not applied it yet. So these two go away, and luckily 7 minus 7 is 0. So the numerator is only 7 natural log x. Let's see the denominator, natural log x. X times 1 over x is 1 plus minus 1 over x. I distributed 1 over x to get 1, and 1 over x to negative 1 to get this. Now I test the L'Hopital's rule, or test the next step. When x is 1, the top is 0. 0, 1 minus 1, 0. I will apply L'Hopital's rule again. So limit as x approaches 1. The top is 7 over x. The denominator is 1 over x plus, be careful, this is a very important rule, so plus 1 over x squared. Good. Now I have to simplify this again before I do anything else. Or I will plug it in, I realize there is nothing else left. So 7 over 1 is 7. 1 plus 1 is 2. I don't even need to simplify anything. I plugged it in. So 7 over 1, 1 plus 1, 2.
Okay, thank you.
Thank you.